Today we are going to talk about free energy, and I'm going to talk about what it is, why do we care, and introduce techniques to calculate its asymptotics as the number of samples goes to infinity. So this is what you see on the board here is kind of what the sequence of steps towards the general free energy, and that's the partition function for the free energy, the negative log of that. This is the steps towards going from a simple things to a simple form of the free energy to something that is much more complicated, that is actually real, that we care about. So, but today, hopefully, we will get to that bottom layer there. Okay, so I'm jumping to the next board immediately. Okay, so let me just write down the goals. So want to remind ourselves. So what is free energy? And why is it called the free energy? Why do we care? Yep, and introduce a core technique or a core observation that is used in the Gray book and using singular learning theory to evaluate singular integral. And the sequence of integrals that we see on the last board are examples of singular integrals. And then we'll hopefully start to climb the ladder. Okay. So what is free energy? Definition: the free energy of a statistical model plus prior pair given, so fixing a set of observation or data set Dn is the negative log of the partition function. Okay, but what is the partition function? Let me define that in the next board. Oops, the opcam is not correct.
Yeah, that's good.
Oops.
Yeah, no problem.
Okay. So to define the partition function, or the evidence of a Bayesian model, we recall that the posterior distribution, well, it's a density on the parameter space W, which we recall is a subset of d-dimensional Euclidean space, is given by this expression. So the probability of some parameter given the observations is the likelihood of observing those observation at that parameter times the prior normalized by something that we call the partition function. So that thing is what we call evidence or partition function. And that's the prior, which will denote phi, and that's the likelihood, which is equal to by the IID assumption, meaning each observation is independent and drawn from the same distribution, known as the true distribution. In that case, it will factorize. Actually, I think that was it was an IID from the Q that from the truth that gives this factorization. It's actually conditional independence condition on the parameter that gives this factorization. Anyway, with that, we can rewrite posterior into the following form, and that will be this will be the notation that we'll be using throughout. I'll define the terms here. So that's the average log loss, which is equal to -1 on n So it's the negative log of that thing, the likelihood. And that is the standard physics notation for partition function. It has many names. It's just a normalizing vector. Well, because the left-hand side is a probability density on W, so if you integrate the right-hand side over W, it should be 1. And with that property makes it the fact that it is you can obtain the quantity by marginalize out the parameter, also makes it the marginal likelihood. So these characterizations give us the expression Zn is the partition function is the integral over the parameter space of the numerator, basically. It is also called the model evidence. So notice that Zn, if we recall from above here, is the probability of observing the data set when we marginalize out the parameter. And this is indeed a probability. So if we integrate it over the observations, it should be 1. So this is it is a probability density over dn, or over the data set. And this probability depends on, if we switch perspective, as we often do with likelihood function, and think of the dn as fixed, and what's varying is the model and the prior, then this is also can be thought of as a likelihood for the model and prior. I think I'm not clear what kind of mathematical difficulties will arise when we are talking about likelihood over a function space. So take that with a grain of salt. And I'm going to erase this part. Whoops. Erasing is not easy, isn't it? Oh, okay, sorry. Okay. I'll erase this part to give the another name for it, which is final name for it, which is the partition function name. Well, that's because it is very much like the Boltzmann distribution in statistical physics. And in that case, we actually call it the partition function. We can rewrite the posterior in the following form, just to absorb the prior into the above. And we can think of this as a Hamiltonian. Well, the temperature term is kind of missing. That's kind of why in the book we generalize to include a temperature term, generalize the posterior to include a temperature term. But for our purpose here, we'll stick with temperature equal to 1, which is the strict Bayesian posterior. Right. So what good is it for? Well, as you can see, it is rediscovered in many different forms. It has many different names. Well, important things have many different names, so and many people care about it. So that's one reason for us to care about it. Another reason is that it is used for example, for model selection. So a really good model, say, so good model. So if I have another model P1, well, on the same parameter space, with its own prior compared to another model P2. Well, if one of them has higher evidence, marginal likelihood, etc., then it is a better model. That's kind of the criterion that is used in Bayesian statistics to do model selection.
I'm going to be a pain and ask you about this. This seems like it sort of depends in some way on the statement you erased, right? The integral over function space being 1. Otherwise, It's not like the different model prior pairs really live in the same universe, except in that statement, right? I guess I don't really understand why I have to accept this as a basis of model selection. Who forces me to do this?
Yeah, so I'm a bit tentative when I say those words as well. So I think one way to discuss this, and I think Watanabe seems to sometimes take this perspective as well, is to introduce hyperparameter. So basically, there is another distribution over the set of model prior pairs, and then you can actually say that the evidence, which is now itself a conditional distribution, conditional on the hyper prior, is the probability of the model prior being is the probability of the model prior given the data set. So in that case, you can say it that way. It's the same kind of difficulty where when we do maximum likelihood estimate. So we are saying that maximum likelihood is the true answer, but really we should be. It's the usual argument is that it's the true answer because it is the most probable parameter. But that's kind of a posterior distribution statement, in which case, if you just put a uniform prior on a space, then then that statement is equivalent to the posterior statement. But yeah, so so there are ways to make this somewhat rigorous, but it's the mathematical difficulties is not mapped out yet.
Thanks.
Yeah. Okay, so let's go to the next board. Okay, just to mention one final reason, well, for us today to care about the free energy. So recall that we've just defined the partition function and the evidence, and the free energy is negative log of that. So Fn is negative log of Zn, just to write that down. Then the Bayesian, the Bayes generalization error is, well, BG. So just to recall what that is, so the Bayesian method of doing statistical estimation is to, so we want to predict the probability of a new observation. Well, one way to do it is to ask what each parameter think of the observation and average that over all parameter. So that's just the Bayesian posterior. That's the Bayesian predictive distribution, and the generalization error is just the KL divergence between this and the truth. Okay, so notice that this prediction depends on dn, which since as such it itself is a random variable. Then theorem, its expectation, well, over the data set, the thing that's giving it the randomness, is equal to the expected increase in free energy of sorts. Let me just write it down and explain. Well, there's this 0 up there, which is a quantity related to the free energy, but it's somehow normalized. So I'm going to have a digression on, kind of a necessary digression on normalization, and I'm going to use a fancy physics word, which don't really understand the full implication, and quenching. Okay, so recall that we now have various quantities that we are interested in. There is the average log loss, there is the partition function, and there is the free energy. Well, these are what I would probably call practical quantities. So once you have the form of your model and the prior, you can actually write down these quantities. And if you have a data set, then these are actual numbers to you. And these are quantities to be minimized or maximized. Maximize. Right. But for theoretical purposes, it might be more convenient to have normalized quantities. And that gives us things like Kn of W, which is given by the quantity from the left-hand side, but normalized by its minima. So this quantity is now, instead of being min-maxed, well, from the left-hand side, this thing is to be minimized. This instead is find it. We wanted theoretically to find its zero, find the zero of it. And the way I write it here, where W naught is in the set of minimum, this perspective kind of generalized to the unrealizable case. If it is realizable, then W naught is W naught is a true parameter, and this just becomes the entropy of the true distribution, the average, the empirical entropy of the true distribution. Please do ask me a question if anything is unclear. And then there is the Zn normalized to Zn naught, which is equal to Zn, but normalized by, okay, I'm going to stick with, the minima formulation. So again, if it is realizable, this is equal to
I'm a bit
Q of
confused.
X.
So
yep.
W0 is the vanishing of the average log loss, right? So why is it really true that ln W0 has to be Sn? Oh,
no,
okay.
The average log loss. Sorry, I think I have a slightly different terminology. So it's the vanishing. W0 is the vanishing. It's the minima of L of 0. The L function, which is just
Okay.
that thing. But if it is realizable at W0, it is just equal to Q, P of X, given W is equal to Q, then that becomes the entropy.
Okay.
Yeah. So it's equal to Q if realizable. And then the quantity above, said in the theorem above, Fn naught is just the negative log of Zn naught, which is equal to Fn, the unnormalized thing, normalized by that, which again becomes Sn, the entropy, empirical entropy, when it is realizable. So these are theoretical quantities, and in fact, there is another operation we can do on these quantities, which is called quenching, of which this L of W quantity is one of them. So basically, instead of looking at, so the quantity above here are stochastic. So the whole first row are stochastic. And the bottom row will be things that have been taken expectation of. So stochastic things has been averaged out, and what's left is kind of their central mathematical quantities that is, as you can tell, probably useful for mathematical analysis, where so the ln becomes ln is the first ln is a random variable depending on the data set, and you take the expectation over the data set and you get this quantity. The other two quantity though is not is actually not named, but I will just write out their form of what quenching meant in that case. So Zn becomes that quantity for which this goes from Ln to L, and there is the negative log of the same for F. Well, these quantities can themselves be normalized or quenched from above. And you get the quantities that we care about today. And it's the KOW quantity that we have been talking about for a while, which is the KL metric on the parameter manifold. And there are two other things, which is the Zn and Fns. That's normalized and quenched from the three quantities on the top left. And that's equal to e to the negative n kW integrate over that manifold against the prior. So that you can either think of the Ln on the left get normalized, or you can think of the above Kn, the stochastic version, and get quenched. And Fn is just negative log of Zn. Okay, so we are going to focus on that today. We will focus on how to evaluate that and how to relate this mathematical integral to their stochastic counterpart. Let's go back to the first board. Okay, let me clear that. Okay, the upshot is we study the normalized and quenched quantities as a first step to understand the practical quantities and how they behave when we actually do statistical learning with real data. Well, let's look at some easy result on the relationship between these two kinds of quantities. We have a theorem which is easy-ish, not too hard to prove. It's theorem 6.4 in Watanabe's book. It states that the stochastic version, the practical stochastic version, when normalized, the free energy, the stochastic version of free energy when normalized, is bounded above by the quenched version. This just relies on Jensen's, I believe that's how it's pronounced, inequality. So that's not too hard to prove. I think one can have a look at that in Watanabe's book. Well, the stronger result that we actually want is that the above quantities they are asymptotically equivalent. So not only is it bounded above by the quenched quantity, asymptotically as n goes to infinity, they are of the same order of magnitude. They're of the same order of magnitude, right? And that's kind of the main, sort of summarized by the main theorem 2 in Watanabe's book, and I will just write out what it meant in our context. Is that quantity above is equal to lambda log n minus n minus 1 log n plus something, and that thing is order 1. So which means that the first two terms are the leading order terms, and the lambda is the RLCT, and that's the order. A corollary of this theorem is that recall above that we have that is equal to the increase of free energy. Whoops. And using the formula above, you can extract the leading order term, and that's lambda on n plus something that decreases way faster than 1 on n. Okay. So we want to get to this result, and we are going to take literally just the first step today. Let's start that on the next board. Oops. Yeah, okay. Right. So we want to evaluate Zn. Let me write it out large and clear, equal to that expression. Okay. Now we are going to introduce a core observation that makes this work, which I think is kind of a genius innovation in SLT. That's equal to, so I'm going to rewrite this term here by using the Dirac delta distribution. So that term, that underlying term, has turned into this integral, where the delta is the Dirac delta distribution. I'm going to put on a physicist hat here and not sort of define this rigorously for this talk. So the idea is that for any particular value of W, this K of W is just a single number, and the Dirac delta, the defining property of the Dirac delta is that you replace anything. It is kind of the evaluation. So so delta x f of x is equal to f of 0. It evaluates the function that you need to integrate against at at 0, and change of coordinates, shifting of coordinates makes it makes these two expression equal. And then there is, if you swap the integration order.
Maybe it's just worth saying that such a distribution exists. It's not trivial to construct. It depends on, for example, the fact that most fibers of K are regular and so on. So there's some work there, but that's not the subject of today.
Yeah, so that's definitely not, not trivial to define. And the next operation is also not trivial to justify, is the fact that you can swap the integral. So if you swap the integral, you get this expression, and that is what Dan introduced last time. That's the density of state. Where K is treated like K is positive, it's treated like an energy function. And we call that V of t is a function of t. And that operation there, integrate against that, is the Laplace transform. Okay. Well, the next observation is that that density of states itself can, if we do mailing transform on the density of states, and the mailing transform of a function f is defined to be the following integral transform. So if we mailing transform the density of states, we get so remember that V of t is the density of states is itself an integral, and if we substitute in the integral above and again swapped the order of integration, a lot of justification required, we get tau of t minus k of w t to the z dt, and that's equal to the zeta function of our model. And the point is that this is easy. Well, if k of w is normal crossing. And I will illustrate that with an example. Let's go to the next board. So let's look at all this in action using an example. This is example 4.7 in Watanabe's book. We have k of x1, our KL metric function is just given by that, and our prior is given by something that is extremely simple. It's just uniform, the uniform distribution, the uniform density on the unit square and 0 elsewhere. Well, in that case, our goal, the Zn function that we would like to evaluate, reduce to this integral over the unit square. And we want to know the asymptotic behavior of this as n goes to infinity. By the way, if you Taylor expand this and then integrate term by term, well, it is not the asymptotics as n goes to infinity, because that works for n small, not n large. So that's the the first thing I tried and didn't work, and now I know why. So let's use the technique that we've been looking at. just moments ago, we first evaluate the zeta function. So the zeta function in this case just becomes so that's k raised to the power of z, and integrate over dx1 and dx2, and notice that it factorizes into two integral. And you can evaluate those independently, and that's just equal to, both of them are equal to 2z plus 1. So there's two of them, so 2z plus 1 squared. Just to make the complex structure clear, let's write it this way. And clearly there's a pole at -1/2. Well, now we can, next thing to do is to find the inverse Meiling transform, because as we recall, that gives us the density of states function, which we will then Laplace transform to get the Zn integral that we want. To find the inverse Meiling transform, one can look up a table of Meiling transform and its properties to massage it into that form, the form of the zeta function. So someone has done that, and that's the lemma. So the Meiling transform of the following function, 1 on m-1 factorial. It's going to be a complicated expression, but bear with me. Multiplied by log of a on t to the m-1. So m is a natural number, and a is a number greater than 0. Lambda is another number greater than 0. And this function is defined like that for t between 0 and a, and f of t equal to 0 for t greater than a. Then the Meiling transform is given by f of z equal to a to the z over z plus lambda. So the proof, okay, I'm actually not going to subject you to the calculation, but so look up table of Meiling transform, or integration by part, which is kind of how some of the properties of the Meiling transform is derived anyway. So you can just write down the Meiling transform of the above function, integrate by parts, and you will get the expression. So let's go to the next part and see what that means for us. By the way, that lemma is given in that generality because that's the only Meiling transform that we are going to use for all our transform needs, at least when our KL divergence is normal crossing, which is guaranteed by resolution of singularity, and that's next time. But for now, what this means for us is that our density of states function for our example, remember it was our zeta function was that. So that's our m, that's our lambda. So that gives us 1/4 t to the, well, lambda minus 1. times log of 1 on t to the m minus 1. Okay, so that's just t to the negative a half negative log t. And finally, we get our z integral equal to the Laplace transform of v of t so this, if you recall from the lemma, is defined between 0 and a, and our a is just 1 in this case, and the function is 0 otherwise. So the integral below from 0 to infinity reduced to integral from 0 to 1 of the expression above. Right. So we want to extract the asymptotics as n goes to infinity. We will do a change of variable from t change to t on n, which gives, well, the integration terminal change to 0 to n, t on n to the negative a half, negative log t on n, and e to the negative t dt. And we can start pulling out n's. So there is there's a root n in here. So and there is a, oops, sorry, I forgot. Excuse me. I forgot the Jacobian. The Jacobian is another n. So there's a root n cancelling with 1 on n to give us 1/4 of square root n. And we split. So this term here is negative log t plus log n. So let's write the log n integral first, 0 to n log n dt minus 0 to n t to the negative half t log t this time, dt. Okay, so this term, this first term here will contribute a log n up the front. The second term wouldn't. So our leading term now becomes log n multiplied by the integral, and I'm going to do a trick, which is the integration terminal is going from 0 to n, but let's write 0 to infinity and then shove the rest. So we are splitting the integral from 0 to infinity into two parts. The first part is 0 to n, which is the original integral, and n to infinity, which is something that, let's write it up here. So the 0 to infinity integration is going from 0 to n plus n to infinity. And that, well, the integration region goes to 0 as n goes to infinity. But we actually need something stronger than that. Let's just write it out first. So this t to the negative a half e to the t dt minus 1 on 4 root n. There's no log n term for the second term. Again, do it from 0 to infinity log t. And then shove everything that still has n dependence into a constant, into something that depends on n, into a remaining term. And it remains to prove that this thing is little o of 1 on n. It vanishes faster than 1 on n. So not only does the integration region strings, quick strings, the integrand themselves, well, there's a e to the negative t in there. So as t is forced into the larger part of the real line, the far right of the real line, the integral vanish very quickly. By the way, if someone wants to check my working, I think there's a typo in here for this term in the book. So please do check that and see if there's anything wrong with my working here. So that we have now extracted the leading term. And if you recall the definition of f, f is negative log of this. So the leading variable here is asymptotically negative log of f is half. Okay, I don't have. Let me write it horizontally here. So f is equal to negative log of z, n, which is equal to half log n plus dot dot dot. Yeah, so our lambda, our RLCT is a half in here, which you can compute from the normal crossing form easily as well. Okay, so that's kind of the core technique for evaluating a singular integral like this. For the remaining few minutes, let's go back to the first board, and I will just preview what we should do next to get the full result. So we are at kind of the bottom level. So we have just done a simple example. So this is our example. But the core observation that we made regarding Laplace transform, Mailing transform, and the density of states function is going to be a constant technique that we'll be using throughout. But from this example, we will start to generalize into the form that we want. The next step would be to add variables. So going from this 2-dimension into arbitrarily large number of variables, m variables, but with the restriction that these quantities, so h and k's are vectors of natural numbers, and these quantities, sorry, that's completely wrong. It's h1 plus 1 over 2k1. So these
I'm
quantities
glad I'm
are
not the only person to have done that.
yeah. Yeah. So these quantities are all still constants, and it's equal to lambda, and the zeta function factorized. But then if you the zeta function integral factorized into individual integrals, and but evaluating those integrals give you the same result, and it's just 1 on z plus lambda raised to the m. The next level would be to generalize this even further still, to get to not only have these variables, but we also have something which I'll probably call the irrelevant variables, the y's, and we have the x. The x where their exponents are k's, and the y's where the exponents are k primes, and the Jacobian, the prior and the Jacobian actually is x h and y h prime, and it's just that the lambda from before is actually smaller than the same quantities. but for the for all the prime coordinates. So those are the coordinates that does not contribute to the leading term, so to speak. And then the next step would be to add in some relevant modification so that it starts to look like the partition function that we actually want to evaluate. So this is invoking Watanabe's main theorem 1, which we haven't quite discussed yet. So to get to this step, we probably need to go through main theorem 1 as well. So the addition here is that we add in these two terms. And these are smooth functions. And I will call this sort of partition function, but in standard form. Standard because everything that is relevant for evaluating the leading term is in normal crossing form. And the final level would just be actually getting to the partition function, the normalized partition function. And the innovation there would be we will, well, the expression that we care about is actually, well, it's actually Kn, if you recall, but then we will express Kn as a difference from the quench version. So the quench version is kind of a centralized, the expected quantity of Kn, and we will just express Kn as a difference from it. So we express Kn as K wait. I shouldn't do this live.
Bart is getting signs right, always.
Yeah. So is it minus K plus K? But anyway, so we express it as a difference. Sorry. Okay. I'm just not going to do that. So K and plus root n beta. And so there's also dividing out by K as well to make sure that things normalizes so that central limit theorems and stuff can apply. So I'm not. We should go when we discuss main theorem 1. I will go through that carefully. So
as long as the idea here is clear that you replace Kn by K plus the difference between Kn and K, and that's a random variable, and then and then this C is introduced to be that random variable. I mean, with the square root taken out. Yeah.
Yep, exactly. So what we're doing here is that we have K, but then it is not in normal crossing form, but we have resolution of singularity that guarantees that in every local coordinate it is a normal crossing form. So there is a resolution map G, so that in every coordinate chart, so the coordinate chart is labeled by alpha. In every chart, if you compose with the resolution map, everything here becomes normal crossing. And also that this function there is actually depending on n, is a smooth function on the pullback, on the manifold pullback by the resolution map on the blowout space. And everything here is normal crossing, and there is the sigma alpha here is the partition of unity that allows us to integrate chart by chart. Okay, that's the kind of the general form that we want to get to. And I will stop there. Sorry to be a bit over time. Any
That's great.
question?
Thanks.
No worries.